guess things remain as planned, and I hand over to Alexei for the first afternoon session.
All right, thank you very much, Marco. It's great to start this afternoon session. My name is Alexei Petrov from Wayne State University. I'll be chairing this session. Our first speaker today is Haiyan Gao, representing Brookhaven National Lab, and she'll be talking about the Electron Ion Collider. I'll give you a 5-minute warning.
Thank you. Good afternoon and good morning, good evening. I would like to thank the organizers for the opportunity, for the invitation to talk to you this morning or this afternoon about the Electron Ion Collider. And so the study of the structure of visible matters has always been at the heart of the modern nuclear physics, for nuclear physics. And understanding the structure of nucleons, which are the building blocks of atomic nuclei, and the nuclei from the theory of strong interaction, namely QCD, in terms of quarks and gluon degree of freedom, has always been at the frontier of modern nuclear physics. Currently, in the United States, there are 2 facilities which are operated by the Department of Energy for QCD. For this kind of studies. One is the relativistic heavy ion collider at Brookhaven National Lab, where the quark-gluon plasma as a perfect liquid was discovered, and also where cold QCD physics, for example, the gluon spin contribution to the gluon spin contribution to the proton spin was also measured. And another facility is Jefferson Lab, which is an electron beam facility, and the energy has been upgraded to 12 GeV, where our study of the nucleon and the nuclear in the valence quark region is focused at. And the community has also been planning for a future QCD frontier facility, namely Electron Ion Collider. And this has been in the planning for actually quite some time. As you can see, the first time it was discovered in a very prominently was in the Nuclear Science Advisory Committee Long Range Plan in 2007. And then it was highlighted as the next future major facility to be constructed in the Long Range Plan 2015. And National Academy of Science released a study to assess the scientific case for the Electron Ion Collider in 2018. And here just highlight the 3 key questions this facility will be able to answer. And the critical decision 0 was announced in January 2020, almost, a little bit more than 2 years ago. And last June, CD1 status was achieved for the project. And this is a partnership between Brookhaven National Lab and Jefferson Lab. So let's take a quick look at the EIC physics. And one important question we would like to answer is the nucleon property in terms of mass and the spin, where they, how do they emerge from their interactions? And we also wanted to study, how does the confined hadronic state emerge from this quark and gluon degrees of freedom of QCD? And also, how do quark-gluon interactions create a nuclear binding? We also wanted to study high gluon density in nuclear to see whether there's a gluon saturation or not. So the proton spin crisis, or we should say puzzle, has been around for quite some time. And in the last several decades, major progress has been made in terms of understanding experimentally and theoretically the proton spin contribution due to the quark, helicity of quark spin, and also gluon. And with the Electron Ion Collider, one can see the kind of improvement in our knowledge about the quark spin contribution to the proton spin, as well as the gluon contribution, gluon spin will be significantly improved. At the same time, well, we currently already know that the orbital angular momentum contribution is important. And with the Electron Ion Collider, we will also be able to study the orbital angular momentum contribution of both the gluon and the quark to the proton spin. And the approach which help us to probe this very important information as well as the rich QCD dynamics is through the 5-dimensional Wigner distribution, and which has the longitudinal momentum, 2-dimensional transverse momentum, as well as 2-dimensional transverse coordinate. And one can integrate either the transverse momentum or the transverse 2-dimensional transverse coordinate. So that will give you either the transverse momentum dependent pattern distribution or the generalized pattern distribution. And together they actually provide the 3-dimensional tomography of the nucleon, which will really provide a very detailed and understanding of the QCD. So in the TMD case, one very powerful approach is to use semi-inclusive deep inelastic scattering. So in this case, in addition to detect the scattered leptons, one also tag the leading hadrons. And in the case of TMD, you do exclusive measurement, whether it's, for example, deeply virtual Compton scattering or deeply virtual meson production. So what is very interesting and also unique at the EIC is that one can do a gluon imaging by looking at, for example, J-psi production from deeply virtual J-psi production. So here just show you some picture which tells you the kind of rich internal structure of the atomic structure inside the nucleon. So the picture here shows the U quark and D quark transverse momentum distribution, and you can see that they are distorted and they also look different. So if one do semi-inclusive measurement by looking at the K-on and D meson, you can also take this kind of image of the strange quark and charm quark inside. So here show you the distribution in the impact parameter space, which from the GPD measurement. So you can see here that in a transversely polarized proton, you can see the C quark distribution. This is the unpolarized case, this is the polarized case. So you can see the kind of difference. So with this machine, we will be able to do this kind of 3-dimensional, whether it's a 3-dimension in the momentum space or 2+1 with 2 in coordinate space, 1 in momentum, this kind of tomography. And another very interesting question has to do with the proton mass. As we know that proton mass actually comes mostly from the interaction from the energy, so not from quark mass. And there has been a lot of study and recent development. In this particular case, one can look at the proton mass decomposition in the proton reservoir in terms of quark energy, quark mass contribution, gluon energy, and very important piece is so-called quantum anomalous energy, which set the scale for the hadron mass. So these 3 components or pieces, one can actually get information from lattice. You can also get information from experimentally determined PDFs and also pi and sigma term. And then for the anomalous energy contribution, there has been a study from the lattice, but experimentally it is extremely interesting and important to probe this particular piece. And what has been proposed is that one can do near threshold quarkonium production, such as J-psi and upsilon production. And at Jefferson Lab, J-psi production near threshold will be measured with high precision at electron ion collider, and this is the precision one predicts with upsilon production near the threshold. Another very interesting physics example is so-called low X physics. As we know, when you go to higher energy and lower X, the gluon contribution or gluon momentum distribution or the gluon density becomes larger, but this actually cannot go forever. So as you go to high energy, you have more and more gluon emission, but due to the unitarity constraint, so it has to come down at some point, so that the question is, the gluon recombination will take place, and that can slow down the gluon emission. In the end, you reach the kind of place where the gluon density is saturated. So how experimentally one probe that? And there has been experimental evidence for gluon saturation, but electron ion collider really will allow you to really study this with a very high precision, and also has the advantage when you use a heavy ion in this case, a relativistic heavy ion, so electron and heavy ion collision. So that actually enhance the kind of saturation scale. So one can reach the kind of gluon saturation region sooner. So these are the just some of the highlights of the EIC science. And so in terms of the machine, the center mass energy for the machine, we need to reach, which is 20 to 140 GeV. And we need to reach higher luminosity, 10 to the 33 to 10 to 34. And highly polarized beam. So in this case, electron will be polarized, and we will have a polarized proton, as well as polarized helium-3 ion as an effective polarized neutron beam. And we also have a EA program, so that we will go to uranium, as high as uranium. And the design will allow for two interaction region. So here is just the schematics, and we will be using the RIC ring to modify that for the hadron ring, and of course there will be a electron or storage ring needs to be built. So here show you for different physics the kind of requirement in terms of center mass energy and the luminosity, and there are different approach try to optimize the machine parameters for the physics we wanted to achieve. And I also want to share with you that the EIC users group community, which was established in 2016, so soon will be 6 years, and has been extremely active and effective. And there are more than, there are about 1,300 PhD members from 34 countries and more than 250 institutions. And of course, we always welcome new members. Here just show you how the EIC users are located in the world. And the user group has been very active, and also the structure is well in place, defined. And one important undertaking on the users group completed was the yellow report, which I will mention on the next slide. And the yellow report was for the detector of design, and also this was 2020, and the user group took 1 year. Everybody worked very hard to produce this yellow report. And there have been annual user group meeting, and due to COVID, more recent meetings have been remote or online. And so in addition to the yellow report and developing EIC detector collaboration proposals, the users group has also been very active in the SNOMAS activities that is undergoing.
4 minutes.
So here is the yellow report, and this report lay out the physics case for the detector requirements and also the evolving detector concept. And the report was released almost exactly 1 year ago, last year. And shortly after that, Brookhaven National Lab and Jefferson Lab together issued a call for proposal, and the proposals were due last December. And here just a couple of pictures to show you the yellow report, the conceptual detector layout design based on the physics I very quickly describe to you. And this is just one view to show you the various detectors. And here is another view to show you the conceptual detector layout. And so what was planned or designed in this yellow report and formed the base for the conceptual design report for the EIC project, and which was used for the CD1 review. And as I mentioned, the review was successful, and we achieved CD1 approval status last June. And I also mentioned that last December, the proposal call for proposal, the proposal were due last December, and 3 collaborations submitted 3 very strong proposals, and these are the Athena detector proposal, and I apologize for the small font, and Cori, a compact detector for the EIC, and the ECHI, EIC comprehensive chromodynamics experiment proposal. And the first EIC detector proposal advisory panel meeting took place last December, and all these three collaborations are presented, did a very good job presenting their case. And the follow-up meeting of this panel will take place next week. And the report by the panel is due March 1st, 2022. Okay, so so here is just to show you the reference schedule. We have achieved CD1, and the next major milestone is CD23A, and that is scheduled for April 2023. And follow that will be CD3. And here show you the early CD4A and CD4 completion dates near the end of FY30 and FY31. These are the early completion dates and the early CD4A, CD4 dates. And the CD4A, CD4 are here, shown here. And the hash area shows the contingency. So here just show you, this is the US Department of Energy CD schedule for this project. And it is, depends on the budget. And so overall, we are looking at, so we are FY22 now, right? So the next 7, 8, 10 years are extremely exciting, and also a lot of hard work ahead. So let me just give you a quick and short summary. EIC is the next QCD frontier with compelling science. And we have a very strong international EIC user community, and which continues to grow. And we have made major progress with the project CD1 approval in June 2021. And there are we have received 3 strong EIC detector proposals, which are currently under review. And there are challenges from different fronts, and budgetary uncertainty certainly is a major one in US with the kind of annual budget cycle. And currently we are still in continual resolution. And there are also technical challenges in terms of reaching the kind of luminosity we would like to achieve, as well as building the detector that will, deliver the science outlined both in the EIC white paper and the National Academy Science Assessment Report. And we welcome new groups to join, and of course also welcome international in-kind contributions. And thank you very much for your attention.
Thank you, Haiyan. Appreciate your talk, very thorough. I see we have one question. Maxime, please go ahead.
Yes, thanks a lot for this very nice talk. I have a question concerning that some time ago there was a discussion of the opportunity of stimulus funding, which from the Congress, which can provide extra funding for different EIC projects, for different DOE projects, including EIC. What is the current status of this? Was some news in this development?
Not at this moment. Before the holidays, in the Senate version of the, I think it's called BBB, Build Back Better. And so there is funding for Office of Science for construction project, and specifically there also in that version there are also specific amount for nuclear physics, for high energy physics, and for other areas of Office of Science. But to my knowledge, this has not been approved yet. So this actually, you asked a very good question. There is enormous uncertainty. We could be in a situation we find suddenly we have a lot of money, which is a good problem to worry about. But we also, we could be in a situation where we find, even to meet the kind of approved funding profile, we have challenges with that. So it's very uncertain. And currently the continuing resolution, at this moment, we're looking at February 18th, but we were advised also to think about the scenario where the continuing resolution is for the entire year. So what can I tell you? All I can tell you is very uncertain.
Okay, thank you.
All right. I don't think we have any time for more questions. So I suggest that people, if you have questions, use Mattermost. For instance, I will have a question on flavor changing lepton interactions with EIC. So please use Mattermost to ask your questions. The next speaker is Christian Ohm from Swedish Royal Institute of Technology and Oscar Klein Center. He'll be talking about future experiments at the energy frontier. Please go ahead, Christian. I'll give you a 5-minute warning.
All right, thank you very much. So thanks very much to the organizers for giving me this opportunity to talk about the exciting future experiments planned for the energy frontier. So it's quite a lot to cover in 20 minutes, so I'll jump right in. The Standard Model has withstood, of course, decades of experimental tests, but since it has several severe shortcomings, it can often feel like it is frustratingly successful. But this means that we're at a really exciting stage, and there are several indications that we could be close to poking a hole in the Standard Model and enter an era of discoveries. So the particle content of the Standard Model was, of course, completed with the discovery of the Higgs at the LHC. But are its properties and couplings exactly as the Standard Model dictates? Is it elementary or is it composite? So scrutinizing the Higgs sector in detail is really the highest priority, and it could reveal discrepancies with the Standard Model and guide towards more complete theory. So shortcomings also indicate that the Standard Model is likely only a low energy effective theory. So it needs to be tested at the highest energies that we can achieve. And there are several good reasons why physics beyond the Standard Model could be lurking around the TeV scale. And such discoveries, of course, would revolutionize the field. So to achieve these goals, new facilities are needed in the coming decades. And since colliders take decades to construct and commission, the planning needs to happen now, and large planning efforts are organizing the community for these big decisions. So the European strategy for particle physics was updated in 2020, and the SNOMAS process is underway in the US and will result in reports with future priorities during this year. So the time period considered here is really very long. And so to get a feeling, I put a timeline at the bottom showing that a person born today would start to near retirement age at the end. So we really have a big responsibility here to plan for the next generations to be able to continue and answer some of our most fundamental questions. So the European strategy from 2006 and the update in 2013 focused on the LHC. And now the focus is to plan for the post-LHC era. So I lifted out a few quotes from the updated strategy that points out that the high Lumi LHC, which is approved and funded, is the highest priority for the near future, followed by an E+E- Higgs factory, and in parallel, R&D on accelerator technology for high field magnets, and also to do technical and financial studies of the feasibility of a future hadron collider at 100 TeV or more. So the inputs to this process were compiled in a briefing book, a comprehensive summary of the physics at these proposed new facilities. So electroweak, strong, flavour, neutrino, BSM, dark matter, dark sector, and the status and challenges for the technologies that are needed for the accelerators, and also the instrumentation and the computing, as we heard in this morning's R&D session. So let's look a little bit at what we should expect. And we start with a snapshot of what we should expect from the high Lumi LHC. So like I said, it was fully approved in 2016, and the construction is now underway. And the current, still current official schedule, we're right now a little bit past the middle in this picture with run 3 about to start, and high Lumi LHC plan to start with run 4 after long shutdown 3 towards the end of this decade. And it would then run throughout the 2030s. So we can place this on our timeline here. It will run at 14 TeV and produce a total of 3 to 4 inverse out-of-barn each in the ATLAS and CMS experiments. And this is 20 times more data than we have at the moment. So it's really most of the data that will come then. And the higher luminosity means that the pileup level will increase dramatically to 140 to 200 individual pp interactions per bunch crossing. And this makes it really a lot more challenging to measure the interesting ones. This necessitates then to do substantial upgrades to the detectors to not degrade the physics performance. So let's have a brief overview of these ambitious upgrades. So both experiments will invest in all new silicon-only trackers that are needed to cope with the increased pileup and also the harsher radiation conditions, and provide extended coverage and pseudo-rapidity. So most of the readout electronics, as well as the trigger and the data acquisition systems, will be replaced to be able to more precisely pick out the interesting events and also to save more of them. So new precision timing detectors will timestamp charged particles with a precision of about 30 to 40 picoseconds. And here Atlas focuses on the challenging forward region and pileup mitigation, and CMS focuses on full barrel coverage out to 8 of 3 with time of flight capabilities for physics and particle identification. So CMS also improves their forward calorimetry with a high granularity calorimeter capable of detailed shower reconstruction. And also here they have help from precision timing information. So these are just some quick highlights, and you can find a lot more information about this in the linked TDRs for each of these little boxes here. And many upgrades are affected, of course, by the pandemic, but the collaborations are really working incredibly hard to meet the very challenging schedules to be ready on time. So let's have a look at the physics then and start with the expected sensitivities in the Higgs sector. So one of the highest priorities at the high-Lumi LHC is to measure the couplings and the properties of the Higgs as accurately as possible. So the sensitivities that were put together in this briefing book were primarily based on results from the partial run-2 analyses using 36 inverse femtobarns from the LHC in run-2. And they were then extrapolated to the full high-Lumi LHC dataset, making assumptions on how different uncertainties would evolve, and also how well the phase 2 detector upgrades would mitigate the increased pileup. And these were then combined in a CERN yellow report, which was then sent as input to the strategy update process. So the Higgs mass is expected to be determined with the 10 to 20 MeV resolution, and most of the main production and decay channels can be determined to 5% or better. And this can be translated to sensitivity on the couplings that are expressed here in the plot on the right as uncertainties on the multiplicative coupling modifiers, kappa. And they reach even below 2% here, you see, for the photon, the W and Z, and the tau couplings. The red bars show the theory uncertainty and how they contribute, and they actually dominate for several. So progress also on the theory side is critical for getting the most out of the high-Lumi LHC. Also, direct searches for invisibly decaying Higgs is a great probe for beyond standard model physics, in particular scenarios where the Higgs decays to dark matter particles. So in the standard model, the branching ratio to neutrinos is about 0.1%. And here, the expected 95% confidence limit for CMS is shown as a function of the offline threshold for missing transverse momentum, reaching typically 5%, you can see here, for a broad range of thresholds. And it shows that it's important to keep the trigger thresholds down also at the increased luminosity. And these studies are continually being updated, or at least every once in a while. And Atlas recently released a new projection using, based on the full run-2 analysis for VH production, where the Higgs decays to heavy flavor quarks. The plot here shows the case to charm quarks, which is very challenging to observe. And here, refined flavor tagging and making use of the new phase 2 tracker gives significant improvements to the C-jet identification, which allows to set upper cross-section limits that are kind of approaching the standard model now, here reaching 6.4 times the standard model when you combine the different 3 channels here. The Higgs self-coupling is the next area here, and it's really a deeply fundamental parameter. It tells us about the shape of the Higgs potential and allows us to probe the nature of the electroweak phase transition early in the universe. So this connects to important questions in cosmology and potential gravitational wave signals that could be detected in the future. And this trilinear coupling here is shown in the diagram in the upper right. So we can measure this important parameter by measurements of di-Higgs production. The cross-section is small. It's about 1,000 times lower than for single Higgs, but it can be probed at the high-Lumi LHC. And di-Higgs analyses are therefore a flagship of the high-Lumi LHC physics program. The self-coupling and the di-Higgs cross-sections are sensitive to many types of beyond standard model physics. So the sensitivity is studied as a function of the coupling modifier. And here, this one is called kappa lambda here. So the plot here is from the 2019 yellow report and shows the expected likelihood when combining Atlas and CMS. And if we read this off at the 68% confidence level, we see that the expected uncertainty is about 50% on this coupling. And the expected significance for observing the di-Higgs process is about 4 sigma. So several channels contribute here, but as you can see, BB gamma gamma and BB tau tau drive the sensitivity. And also the di-Higgs studies continue past the yellow report, and there are 2 new projections here also from Atlas that were recently updated based on the results and methods used in the full run-2 analysis. So on the left, we see BB tau tau sensitivity, which has been revisited. And the expected significance of observing di-Higgs production in the BB tau tau channel alone is shown here. So the previous expectation was 2.1 sigma, assuming the standard model, so at this kappa lambda equal to 1. And now it reaches 2.8 sigma with improvements in the analysis and also refined tau and B-jet identification. On the right, we see how improvements in the BB gamma gamma analysis leads to improved 1 sigma confidence interval for kappa lambda. So this is now at 0.3 to 1.9 in this channel alone. So you could probably expect to see a few more of these results being updated to come out from Atlas and CMS for the SNOMAS process in the coming months. If we look at other sectors of the standard model, measurements of vector boson scattering can also probe the mechanism of electroweak symmetry breaking, since multi-boson processes are sensitive to gauge couplings. And this projection for CMS on the left shows the expected uncertainty on the cross-section measurements for same sign WW and WZ, reaching around 10% and 5% respectively, if you read off at 3 inverse out of Barnes here. So the middle plot shows that the expected significance for observing longitudinal WW scattering is now 4 sigma. And this is an important process also because it gives an indirect information about the Higgs coupling with vector bosons. In the top sector, measurements of many rare processes will become accessible. So on the right, you see a 4-top production clearly visible in a signal region. Here showing the HT distribution in a signal region with 3 leptons and 6 jets, out of which 3 are B-tagged. So the recent observed significance of 4.2 sigma for this process already in run 2 makes this extra interesting to look closely at and perhaps consider doing differential measurements. Okay, so of course, since the High-Lumi LHC is exploring the energy frontier, there are also lots of opportunities to discover beyond standard model physics in direct searches. And on the left, we see expected sensitivity for exclusion of electroweak SUSY scenarios with the pure Higgsino LSP, where the compressed mass hierarchies give soft leptons. And you can see in blue here, the sensitivity of an analysis that uses these soft leptons to find these scenarios, and even sensitivity at the bottom to even smaller mass differences below 1 GeV or so is achieved by exploiting the challenging disappearing track signature from a long-lived chargino that decays kind of partway through the tracker. We can also expect sensitivity gains proportional to the luminosity increase in searches, in particular for searches that have unconventional signatures and therefore very low backgrounds. And for some of these, the detector upgrades provide even more sensitivity boosts. So what's shown here on the right is a heavy penetrating long-lived charge particle where the CMS MIP timing layer can measure time of flight very accurately and provide powerful discrimination from the background, which you see peaking very tightly here at beta equal to 1. You can see on the right. So we now switch over from what is approved and funded to proposed facilities that are now being studied as options for the future colliders. And here, some more or less shovel ready if approved, and some are being evaluated in terms of technical and financial feasibility. So I highly recommend looking at Frank's talk on accelerator R&D this morning for much more in-depth information. So there are many degrees of freedom here, of course. Should it be a linear or circular machine? Is the technology ready, or is R&D needed? And if so, how long do we expect it to take? Should we go with E+ E- for precision, or proton-proton for exploration, or both? And questions that include political dimensions, of course, like where it should be built. So let's start by looking at E+ E-, since the Higgs factory is the highest priority. The cross-section for various Higgs processes are shown as function of center mass energy here. And we see ZH production peaking sharply at 250 GeV in yellow. And then VBF takes over for single Higgs production at around 500 GeV or so. And continues to rise with energy. TTH in black turns on steeply at 500 GeV, giving access to the TH Yukawa coupling. And di-Higgs is shown in light blue and magenta here, with cross sections reaching about 1 femtobarn at several TeV, where both diagrams here generate the 2 Higgs bosons through this trilinear coupling. So this gives some guidance of what center of mass energies should be targeted to make measurements of the Higgs properties. So let's start by looking at the 2 most mature proposed linear E+ E- collider. So the International Linear Collider would be built in Japan using superconducting RF cavities to achieve a center of mass energy of 250 to 500 GeV, but also upgradable to 1 TeV by extending the tunnel from 20.5 to 31 and finally 50 kilometers. The compact linear collider would be built at CERN, starting at 380 GeV, going up to 1.5 and 3 TeV by extensions up to 50 kilometers. And it can reach these higher energies through a novel drive beam technology shown in this little animation. You can see at the top where a high power but low energy beam is accelerated. And at the bottom, the E+ E- physics beams start. And then as they reach the main linacs here, the drive beam generates high field gradients up to 100 megavolts per meter in the room temperature RF cavities. So both of these could be operational in the first stages in about 10 to 12 years if they were approved today. Of course, for exploring the energy frontier, circular PP machines are very powerful, and 2 PP colliders in 100-kilometer tunnels have been proposed to follow the High-Lumi LHC. So FCC-HH at CERN is designed for a center of mass energy of 100 TeV with 16 Tesla dipoles, and the SPPC in China reaching 75 GeV with 12 Tesla magnets. So these high field magnets require both R&D on niobium-3 tin superconductors, a tricky alloy which is a bit more brittle than niobium titanium used in the LHC, and prototyping also. And each of these stages would take a while, so they would likely not be ready for production for 20 to 30 years. So of course, the tunnel could be built earlier and used for an E+ E- machine in the meantime. So in these long tunnels, very interesting energies can be reached without running into too large problems with energy losses because of synchrotron radiation, and at very high luminosity, and also reach very high luminosities at lower center mass energy. So the circular collider options therefore include E+ E- precision machines as pre-stages for the PP machines. FCC-EE at CERN reaching 365 GeV, and CEPC in China reaching 240 GeV. This also makes for more feasible cost profiles, of course, to build the large tunnels needed for the proton machines later. Very large data sets with W and Z and Higgs bosons can be collected in the E+ E- machines, which are very powerful for electroweak precision measurements. So I also want to mention the feasibility studies for muon colliders that are really moving forward, and they could be a both power efficient and compact option for both multi-TeV exploration and precision measurements. So there's a backup slide about this. And so let's have a look at some. Okay, so let's have a look at some of the physics highlights of these new proposed facilities then. So I'll show examples of the briefing book, from the briefing book, so covering ILC, CLIC, FCC-EE, and HH, and also CEPC. First, let's look at the Higgs couplings. So here you see High-Lumi LHC in light gray, and the main options discussed earlier, FCC in blue shades, CEPC in orange, which is of course very similar to FCC-EE at 240 GeV. CLIC in red, ILC in green, and generally for each one, the darker the shade, the higher the energy where there are upgrades. So as we saw earlier, High-Lumi LHC is expected to determine all couplings down to a few percent, except for charm, which is right in the middle here, where there's no sensitivity expected. But this will reach a few percent uncertainty with all the E+ E- options. The other couplings which see the biggest improvements are, for example, for W and Z and for bottom. All the E+ E- options provide significant and quite similar improvements. For the TH couplings, both sufficient center of mass energy and luminosity is needed, so only upgraded ILC and CLIC and also FCC-HH are expected to make significant improvements here. The two rightmost plots here don't show the coupling sensitivity, but show 95% confidence level branching ratio limits for invisible and untagged Higgs decays, where the invisible branching ratio reaches well below the standard model value in the case of the FCC-HH here. So it's easy to understand that the community is generally very enthusiastic about all of these next possible E+ E- colliders, and many think that the E+ E- machine would be great and the PP should follow. So to a large extent, it's a political decision about the direction to go and what paths it would open up for the future evolution. So we look at the di-Higgs then. Also here, High-Lumi LHC is shown in gray, FCC in blue, CLIC in red, and ILC in green. Here, the center of mass energy is needed for large improvements over High-Lumi LHC, which we said is expected to reach about 50% uncertainty. So ILC and CLIC are expected to reach about 10% with the upgrades. And FCC-EE 365 GeV reaches from 30 to 20. This depends a little bit on how many interaction points are used, if it's 2 or 4. And then if you combine with FCC-HH, you get down to 5%. So electroweak precision observables, like the weak mixing angle, the masses of the Z and the W in the top, and also the Higgs, follow exact relationships in the standard model. So precise measurements of these provide powerful consistency tests of the electroweak sector. And these could be very sensitive to BSM. So what's shown here is the current fit using the best measurements to date in the plane of the two oblique parameters S and T. So I apologize to Deblois and collaborators for distorting the proportions of their plot here a little bit, but I'll show you why soon. So looking at the future colliders then in this plane, high-Lumi LHC in gray gives improvements of a factor of 2 to 3 in S and T. And this is, of course, a lot more clearly seen if we scale things or set things to scale here. So we see that E+ E- machines dramatically reduce the errors on S and T, especially the circular machines planned to run at the Z and the WW center mass energies with high luminosities. Additional improvements from ILC and CLIC are shown if they complement the run plans with the GigaZ runs, and those are showed as the dashed lines that are tiny there in the middle. So this would be a dramatic improvement, which would really be very sensitive to BSM and really test the standard model. Beyond standard model physics, there's really a wide range of BSM scenarios that in the future facilities can probe. But I'll highlight a couple from the briefing book here. The first one is an additional heavy scalar singlet showing exclusion on coupling between this new scalar and the Higgs as a function of the mass of the scalar. And the orange hatched region here has strong first order electroweak phase transition, which is very interesting for baryogenesis, the detectable gravitational waves. And you can see that all of the proposed colliders take out good chunks of this interesting region, and that there is sensitivity from both Higgs coupling measurements and direct searches. So there's sensitivity from both types of measurements here. Okay. So looking at the next one, this shows a pure Higgsino lightest supersymmetric particle, which is an interesting WIMP candidate. So both FCC-HH and CLIC 3000 can conclusively test thermal Higgsino WIMP dark matter, which is quite challenging for direct detection otherwise. So here, center mass energy is needed, of course, so the low energy E+ E- can't easily beat the high-Lumi LHC. So finally, looking at a dark scalar mixing with the Higgs, this gives rise to many challenging signatures, depending on where you are in the parameter space here. So proposed future colliders shown together here with many proposed experiments at the high-Lumi LHC, like Matusla, Codex B, Phaser 2, etc. And these cover kind of the central part of parameter space, but there's complementary sensitivity from future colliders on the right side. Of course, there's a lot more. So I really recommend looking at the briefing book, which does a good job of summarizing sensitivities to many different kinds of BSM scenarios. And there are also several interesting talks during this week, which discusses BSM sensitivity at future colliders. So that brings me to the summary then. So high-Lumi LHC is approved and being constructed, and will explore the energy frontier in the 2030s. It's really critical that this is a success, of course, also for future projects. So there's lots of work to do on upgrades and squeezing the best performance possible out of these to get the best sensitivity that we can from the high-Lumi LHC. It's really an interesting time for HEP with the standard model now complete, but suffering from large flaws. So the European strategy has been updated recently, and SNOMAS is ongoing. So it's really a great occasion to take stock and see where we are, read up a bit, and also get involved in the studies of these future colliders for the long-term future of the field. So I've sprinkled out plenty of links in the slides here. And there are some really, really useful overview meetings from these big planning efforts. And I think it's a really good time to read up and get involved in these decisions. So thank you.
Thank you very much, Christian, for a very comprehensive talk. We have time for one brief question. Anyone? So since there are no questions, I might want to ask, can you say, you said that you have some info about the muon collider progress in your backup slides. Would it be possible to spend a minute kind of outlining?
Yes,
there?
Absolutely. Thanks so much for asking. It was one of those slides that I unfortunately felt that I needed to move to the end to fit into the time. But yeah, so muon colliders are really exciting option, but of course still requires quite a lot of R&D. But here you can see it would be a pretty, really a small footprint compared to E+ E- and PP to reach high energies. And if you look at just comparing muon, mu center mass of 14 TeV, this corresponds to kind of parton center mass energy you get from 100 TeV PP collider. And in this recent paper, it's a 10 TeV, reaching over 10 TeV center mass energy muon collider that has a 10 kilometer circumference. That's shown in this diagram here. But of course, there are really significant challenges. You need to make the muons, typically from protons, and then if you do that, then you have a large spread of momentum for the muons, so you need to cool them. And of course, the muon lifetime is very short, and so you must be really fast to accelerate them. You also need very high field magnets, so there's R&D needed for this. But there has been really a lot of progress in recent years. So the SNOMAS effort, this is being studied more extensively, and I hope that there will be lots of updates in the SNOMAS reports. And there's also muon collider collaboration that is formed. But there's, yeah, on both the acceleration feasibility and also the cooling, there have been these really big improvements in the last several years.
All right, thank you. If there are more questions, please use Mattermost. Let's thank again Christian for a very comprehensive talk. Thank you.
Thank you.
Next speaker is Matteo Palutan from Frascati. Hi, Matteo, I can see you.
Hi, yes.
He will talk about future flavor experiments. I'll give you a 5-minute warning.
Okay, many thanks. So many thanks to the organizer for the kind invitation. I will, in fact, discuss the future prospect for flavor experiments, and I will start, of course, by reiterating what was discussed widely during the conference. That is that the flavor physics give excellent opportunities for unveiling physics beyond the standard model by indirect effect to low energy processes, such as, for example, in rare decays of hadrons, where the new physics is enhanced, sensitivity to new physics is enhanced by the suppression of the standard model amplitude. This requires, of course, huge statistics. The value of the energy scales, which is explored, scales with the luminosity to the power of 1/4. Then there is the need to control strictly the experimental systematics, and then we need the precise standard model prediction, which comes by choosing clean observables, like, for example, the Lepton-Fourier universality ratios, having precise hadronic contribution to percent level with lattice QCD, or choosing null test, like, for example, the Lepton-Fourier violation studies. All in all, increasing precision in flavor physics will allow to probe mass scales which are not accessible to directly to the LHC. Okay, the main players today in flavor physics, both at hadron machine and the plus-minus colliders, are shown here. There are experiments dedicated to heavy flavor experiment dedicated with a wide range of measurement, like, for example, LACB at LAC, or BEL2 and BES3 at the plus-minus colliders. There are experiments dedicated to ultra-rare kaon decays, like Na62 at CERN-RPS and COTO experiment at J-Park. And finally, ATRA and CMS, which have good sensitivity for B-physics channels, especially with muon Nefana states. Of course, since in flavor physics the precision is the key ingredient, the complementarity between the different experimental approach is really the main point for a successful exploitation of this kind of physics. So I will start giving some quick perspective in kaon physics. As discussed by Christina on Tuesday, the focus now is on ultra-rare kaon decays, K plus, pi plus, neutrino, antineutrino, and K long, pi zero, neutrino, antineutrino, which have excellent sensitivity for characterizing new physics. And Na62 recently shown a first evidence of the K plus channel, and are now aiming at 10% uncertainty on the Bianchi ratio by 2025. COTO experiment at J-Park is instead setting stringent limits on the K-long channel, and they expect to have sensitivity of order 10 to minus 11 by mid-2020s. So future perspectives at J-Park can be the extension of the hadron experimental facility, which is presently in discussion with an increased beam power. And this will allow to upgrade the COTO experiment and targeting a K-long measurement with 35 standard model events expected. And this comes via, of course, an increase of beam intensity, an expansion of the fiducial volume, and in particular, a reduction of the background contamination by profiting of the COTO experience. At CERN instead, there is in discussion an integrated program with high intensity K+ and K-long beams proposed to run until the end of 2030s. And this will be made by a first phase with an upgrade of NA62, targeting K+ measurement at 5% accuracy. And this will foresee an intensity increase of the beam of the level at the level of four times the present one, and a much improved time resolution to keep the random variable rate under control, and while maintaining key performance of the detector at a rate. The K-long experiment, the clever detector, is targeting instead 60 measurement on the K-long channel with 60 standard model events, and the beam intensity even higher, a factor of 6, the present one, and optimization of the beam line is required to suppress the relevant backgrounds. All this discussion is triggering, of course, a stronger R&D phase on the detector in strong synergy with the future upgrades of the ILUMI LAC. In particular, for example, there is the study of an upgrade of the GigaTracker with the time resolution below 50 picosecond, and several solutions and the study for the calorimetry. Moving now to the electron-positron colliders, I start from the base 3 experiment, which is running with great success at the Belgian Electron-Positron Collider. And the experiment already accumulated rich samples of D-meson and Charmed baryons, and is planning to extend the data taking until 2030. The physics program is very rich, as reported in many talks in this conference. And one focus point is the study of quantum correlated D0 bar state, which allow to measure very precisely the strong phases in the D0 hadronic decays, which are essential for the measurement of the Ckm or gamma. And in addition, precise measurement of absolute branching fraction of Charmed hadrons are possible at this machine. The future of this program is proposed via the super tau chart factories. And in this case, the goal is to accumulate 1 inverse attobar per year. And this will allow to extend the best 3 program with 100 times the statistics, but also to access chart mixing and CP studies with high sensitivity, the level of 10 to -4, and the physics of tau lepton with measurement competitive with Bell2 with few inverse attobar. So the first proposal is the STCF project in China, which is targeting a luminosity of the order of 0.5 10 to 35 with the electron polarized beam. And the CDR is expected this year. And if approved, this project will start operation in 2030. The competitor project is the SCTF complex in Russia. The peak luminosity is in this case a bit higher. And they started earlier the discussion. This is one of the 6 mega science projects presently discussed in Russia, and there is a running grant with the European Community for R&D. Time scale of the project is similar to the previous one. Moving now to higher energy, and I'm going to discuss the case of Bell2 at the Super KEK-B. This experiment, of course, builds on the success of the Babar and Bell experiment on the B factories, and is targeting a 50 inverse attobar integrated luminosity by having a peak by a design peak luminosity of 6 10 to 35. The Bell2 experiment is a brand new apparatus with excellent neutral reconstruction capabilities, high flavor tagging efficiencies, and the capability to set strong kinematic constraints on final states with neutrino. So systematics quite different from hadron machines, and so full complementarity, for example, with LACB. The data taking very recent, in December, the machine achieved the world record instantaneous luminosity, 410^34. This is a remarkable result. And the plan is to be able to accumulate a bifactory-like sample that is around 1 inverse femtobarn by late 2022. Of course, the low luminosity with respect to the design value is still a concern for the full exploitation of the physics program, and a second shutdown mid-2020 is in discussion for a possible machine upgrade. The physics program is very ambitious and is also based on an impressive detector performance, which is being demonstrated already, and a very, very good analysis preparedness. So on the short term, with the less than 1 inverse femtobarn, the experiment is expected to contribute strongly on the LeptonPhoton universality test with B to D tau nu decays, precise measurement of UV and VCB, and high sensitivity to electroweak penguins and leptonic B rare decays. You see here on the right a nice example for B+, K+, neutrino, antineutrino, where the sensitivity with the 10% of the Bell2 statistics is already very remarkable. On the longer term, with the more than 1 inverse femtobarn, I mean, the tau physics field will be completely open, and Bell2 will dominate this in the next decade. And especially with more than 10 inverse femtobarn, the experiment is expected to confirm or not the anomalies seen by LACB. So we are speaking about a wide physics program with many unique features and in full complementarity with the program at Hadron Machine. So it's really crucial that Bell2 is able to target its final sensitivity. Moving now to the LSE as a flavor machine. I mean, this machine demonstrated to provide unprecedented statistics of heavy hadron decays. Of course, the experiment are challenged by the very, very difficult event topology, and this will become even more extreme at the future ILUMI LAC. Nevertheless, there is a rich program of measurement starting from Atlas CMS. They intend to keep their effort on B physics and especially on CP violation rare processes with muon and Fana states. You see here on the right a combination of the LAC experiment for Phi-S. I have stolen this version from Alex's presentation, where I mean an upgraded standard model expectation is catched. And of course, I mean, there is a real boost expected from combining the result from the LAC experiment where they have similar sensitivities. But in addition, there are new opportunities from phase 2 upgrades with an increased muon coverage from the experiment, and also, I mean, improvements in tracker resolution. For example, here on the bottom right, you see the expectation of CMS on BS mu with an increased mass resolution. But in any case, I mean, the key point will be for Atlas and CMS to keep trigger thresholds which are appropriate for BDKs. Moving now to LACB, future plans for LACB build, of course, on the success of the experiment during round 1 and round 2 for what was expected, BS mu, BS oscillation, time-dependent CP violation, gamma measurement, but also for the unexpected, the hints of LeptonPhoton universality, the importance of charge physics, exotic hadron spectroscopy, and key measurement in the electroweak physics. But what is to be underlined is that the physics program at LACB is limited by detector and not by the machine. So there is really a clear case for an ambition plan of upgrades, which is sketched here on the right. So a first upgrade will come in operation this year, with the target of accumulating 50 inverse femtobarn during round 3 and round 4. And this phase will be really an healthy competition with Bell2 at 50 inverse femtobarn. But a second phase upgrade, so an upgrade 2, is present in discussion for round 5 and round 6, with a target luminosity around 10 to 34 and the goal of accumulating 300 inverse femtobarn during round 5 and round 6. in the present phase, we are in discussion with LACC about this project. One word about the upgrade 1, which is at the starting line. There is an exceptional effort ongoing to deliver all the project components in time to start this year, despite the very difficult conditions. I mean, especially on tracking detectors, we are finalizing assembly and installation, and the system will be completed by end of 22. There are some, one detector in particular will be completed during the year. PID detectors are in commissioning. And one thing which is to be underlined is that we will deploy for first time another machine a full software trig with an HLT1 completely based on GPUs. You see here a few pictures for the various detectors which are in commissioning in preparation. As said, the upgrade 1 will not saturate precision in many key observables, so this is a strong motivation to build the upgrade 2 to fully realize the potential of the machine. And we got strong support from the European strategy on this. Here is a list of key topics and which are discussed in detail in the physics case document linked on the right. I want to show a few examples. First is obviously the potential for testing the CKM paradigm with unprecedented accuracy. You see here on top right what is the expectation after upgrade 2 plus lattice QCD improvements on the unitary triangle, and the bottom right the expected error on phi s, which really approaches the standard model error in both tree and loop modes, which is also very important. But beside that, there is the possibility to probe in the structure of new physics in BSLL decays by comparing muon and electron final states. And you see here on the right the difference of the Wilson coefficient between electron and muons as expected in case of pure vector new physics or vector axial new physics. So there is the real potential to distinguish between the different models. And finally, the upgrade 2 will be possibly the only facility with a realistic possibility to gauge the charm CP violation in mixing with sensitivity close to standard model expectation. So a great potential. Yes. Of course, this comes via a huge challenge for detector. In fact, we are targeting same performances as in Run 2, but with pileup 40. And the design is based on a safe spectrometer footprint, but with innovative technology solution and for detector and data processing. Key ingredients are increased granularity, fast timing, and radiation hardness. There are a number of technology that we need to develop. For tracking, we need a 4D tracking on the vertex detector with a very good time resolution in order to separate the heavy flavor decay vertices and associate them to the correct primary vertices. And for this, we are exploring sensor technology like 3D or LGAD, and we plan to develop 28 nanometer ASICs. For the downstream and upstream silicon trackers, we plan to explore a solution based on monolithic active pixel sensor. On particle AD, we are exploring many options, among which means SPACAL with crystal fiber for the calorimeter, rich with the timing capabilities, time of flight based on quartz plane, and then micro-well for the muon detector. And finally, of course, we need to develop a software trigger which will be fully based on heterogeneous computing, as discussed also this morning. So technology goals are very ambitious, but I mean the time scale is suitable to develop them. And I also would like to say that I see a strong synergy with the future high energy project, and of course new collaborators are welcome. So I'm now to my conclusion. I think it's clear that increasing precision in quark flavor physics will allow to probe mass scales not accessible directly at the LHC. This in strong complementarity with the IPT frontier. Of course, this ambitious goal requires improvements in theory based on lattice QCD. There is a rich and diverse experimental program at the horizon in measurement of ultra-rare kaon decays via kaon beams, both at CERN and at J-Park. Discussion about super tau factories to be built in China or in Russia, and especially the completion of the Bell 2 program at Super KEK-B. And finally, the exploitation of the high luminosity machine as a flavor factory, both at ATLAS and CMS, which will continue their B physics with more final states, and with the LSEB upgrade to fully realize the potential of this machine in the flavor physics. So I think there is an excellent sensitivity for physics beyond the standard model in a context of best using the present experimental infrastructure and is strong with a strong push also on the new detector technologies. Many thanks.
Thank you very much, Matteo. This was a very nice talk. I really enjoyed it. Are there any questions? I hope all of those proposals would come to fruition. I'm actually curious about the tau charm, super tau charm factories. I mean, at the last charm meeting, I think the Russian proposal was modified. So they were talking about moving it from Novosibirsk to one of the weapons labs or something.
Yes.
Which made me wonder if you know, what would be the possibilities for doing international, you know, research over there. I don't know if you have any insights.
Yes, no, I don't have insights on this. I've also noticed this point that now another laboratory is mentioned for this, which will act as a facility in the domain of nuclear physics as well. In general, I mean, my impression with discussion with colleagues is that, I mean, at the moment, the two teams of proponents are exchanging information, are also organizing common workshops to discuss the project. And but at the moment, there is the intention to push the project in their countries to see if it can be approved. We are speaking of I mean, large project, but still of a size which can be afforded at a regional level. And then, of course, depending on how this will develop, I also hope and see that there are opportunities for probably strengthened synergy between this project, because I mean, of course, I mean, having one strong super tau charm factory in the world, I think it's already a very ambitious and nice goal to achieve. Yeah.
Okay, thank you. Are there any other questions? Well, if not, again, I encourage you to use Mattermost. Thank you, Matteo.
Thank you.
Our next speaker is Elizabeth Worcester from Brookhaven, and she'll be talking about future neutrino experiments.
All right, thank you for the opportunity to talk about neutrino experiments. Just as a little disclaimer, this is a hugely broad field. My research is in neutrino oscillation physics, so in the interest of time and actually telling you about something that I know about, that's what I'm going to focus on. And I'm a collaborator on SBN and Dune. So what do we know and not know about neutrinos? We know that they're the neutral leptons. We know they have to have 3 active flavors. We don't know whether there are additional sterile flavors. They have a very small mass. We have limits on the sum of neutrino masses, mostly from cosmology, and the direct measurement limits are also starting to be quite good. We know that they mix. The flavor eigenstates are not the same as the mass eigenstates. The mixing is described by the PNMS matrix, and we have measured all the mixing angles and mass splittings to pretty good precision. But of course, we want more precise measurements. So that's what I'm going to talk about coming up. Neutrinos are detected via their interaction products, which makes things complicated. The interaction cross sections are very small, and the neutrino nucleus interaction model has large uncertainties, which impacts systematics on some of these measurements. And they may be Majorana or Dirac. If they're Majorana, then there's additional CP violating phases that enter beyond the CP violating phase in the PM&S matrix. So this is a sort of single slide picture of what we know about neutrino mixing and oscillation. The flavor states are related to the mass states by the PM&S matrix, which can be parameterized with this 3 different mixing angles and potentially a CP violating phase. So most of these parameters are currently measured to about 3%, give or take. There's a number of open questions though. One is the mass ordering. We've measured these mass splittings, but not the sign of delta m squared 3,2. So we don't know if the 2 that are close together are the lightest states or the heavier states. So that remains to be determined. The octant is very interesting. We know that theta 2,3 is about 45 degrees, but we don't know if it's slightly less in the so-called lower octant or slightly higher in the so-called upper octant, or if it's exactly 45 degrees, which would indicate some additional symmetry. We don't know if CP is violated in neutrino oscillation. That would mean that delta CP is not equal to 0 or pi. And we don't know if we're looking at only 3 flavors, if this 3 flavor picture is complete. And so looking at whether or not this PM&S matrix is unitary is interesting to see if this 3 flavor model fully describes our world. So what can we discover with these kinds of measurements? So first of all, we're interested in discovering CP violation in leptons. And one of the reasons, of course, is just that symmetry and symmetry violation has been a major driver of discovery in particle physics. So it's something we always want to look at. But additionally, we know that leptogenesis requires CP violation in the high energy Lagrangian, which is the Lagrangian that includes the right-handed neutrinos. And so there's no explicit model independent connection between the low energy PM&S CP violation that I'm going to talk about studying today and the high energy CP violation that's required for leptogenesis. But there are some models where all of the CP violation comes from the low energy phase. We're interested in flavor structure. Why is the structure of the neutrino mixing matrix so different from that of the quark mixing matrix? Is there a flavor symmetry that can produce this pattern of mixing, and how is it broken? And like I mentioned, this is the same question as the octant. Is nu mu and nu tau mixing symmetric? And if so, why? Additionally, in addition to flavor, many BSM models also make specific predictions for values of the oscillation parameters. So if we measure these parameters precisely enough, then we can distinguish among models. And so this plot is just an example of that, where the value of delta is plotted for different symmetry models. And you can see that if you make precise measurements like are expected at future experiments, that you would be able to distinguish among these different flavor structures. And neutrino experiments are also good at doing non-neutrino beyond the standard model physics. So there's a bunch of other things that can be done with these detectors, which I'll talk about a little bit. So neutrinos have a huge range of energies depending on the source that we get them from. For this talk, I'm going to focus on reactor neutrinos, which are sort of few MeV scale, astrophysical, such as solar and supernova neutrinos that are, again, low energy, sort of few to tens of MeV. And then for the long baseline accelerator neutrinos, these tend to be, few GeV scale neutrinos. And just as a reminder, the probability of oscillation depends on both L over E and the mass splitting. So different values of L over E are sensitive to different mass splittings and mixing angles. And so experimentally, if we can optimize the baseline or the energy for a desired measurement, that's what we do. So we sometimes choose the baseline to specifically be sensitive to certain measurements. All right, so getting into the details of the future precision oscillation experiments that I want to talk about. The 3 that I want to talk about mostly today are Juno, Hyper-K, and Dune. So Juno is focused on measuring these 3 mixing angles, sine squared theta 1,2, delta m squared 1,2, and delta m squared 3,2, as well as the mass ordering. Hyper-K is focused on measuring delta CP, theta 1,3, theta 2,3, and delta m squared 3,2. These are the parameters that govern long baseline oscillation. And Dune is interested in making the same measurements, with the difference that Dune will be sensitive to the mass ordering in the accelerator part of the experiment, whereas Hyper-K will get the mass ordering from atmospheric neutrinos. And all of these experiments are also going to be studying astrophysics, such as supernova neutrinos and solar neutrinos, and searching for BSM in their data. So to start with Juno, Juno is the Zhengmin Underground Neutrino Observatory. It's a reactor anti-neutrino experiment. So it is a 20 kiloton active liquid scintillator detector that observes anti-neutrinos from 2 nuclear power plants at a baseline of 53 kilometers. This is in Guangdong, China. So it has about a 700 meter overburden, and it has really quite exquisite energy resolution, which it needs in order to do the physics that it wants to do. So this is a plot of the events as a function of anti-neutrino energy. The gray curve here is with no oscillations, and then the blue and red curves show the actual signal that you would expect for normal and inverted ordering. So one of the primary goals for Juno is to determine the mass ordering with something like a little bit more than 3 sigma precision. And in order to do that, you have to be able to distinguish between the red curve and the blue curve. So that's why the energy resolution is so critical. And you can see you're also sensitive to these 3 mixing parameters that Juno expects to be able to measure better than 0.6%. So that represents a significant increase in precision over current knowledge. So moving on to the long baseline oscillation experiments, the idea of these experiments is to measure nu-mu survival and nu-e appearance in a nu-mu dominated beam. And this is just a plot of the oscillation probability for survival in blue and appearance in orange as a function of L/E for 1 GeV muon neutrinos. This oscillation probability depends on delta m squared 3.2, sine squared theta 2.3, sine squared theta 1.3, delta CP, and matter effects. So you have the opportunity to measure all of these parameters in a single experiment, but you have to disentangle the different effects and resolve any degeneracies. So one thing that is interesting about these experiments is that the value of delta affects both the rate and shape of the appearance probability, and it has an asymmetric impact on neutrinos and antineutrinos. So that's just exactly CP violation. So what you see here is the probability of nu-mu to nu-e oscillation as a function of neutrino energy for 3 different values of delta. So if delta is minus pi/2, then the oscillation probability here is increased for neutrinos and decreased for antineutrinos, and then the opposite for the opposite sign of delta. And there's actually a degeneracy between matter-antimatter asymmetry from delta and from matter effects for baselines less than 1,000 kilometers. So that's one of the motivations for going to longer baseline if you want to break that degeneracy. So Kendall talked about the current long baseline experiments earlier in the week. So I'm not going to say anything about these other than to say that they are starting to have some sensitivity to mass ordering and delta. Here you can see the latest results from T2K and NOVA that have, significant information about the ordering and about the value of delta, but we do not yet really truly know the values of these parameters. And the ultimate sensitivity of these experiments depends pretty strongly on the true values. So it's not completely clear exactly where these experiments will end up when they finish their data taking. So moving on to the future long baseline experiments, again, there are 2, T2HK, Tokai to Hyper-K, and Dune, which is in the US from Fermilab to Sanford Underground Research Facility in South Dakota. So these 2 experiments are measuring a lot of the same things, but they have a little bit of a different strategy in how to go about making the measurement. So Hyper-K, the strategy is to maximize statistics and minimize the matter effect to focus on CP violation discovery. And so that leads to the choice of a short baseline of 295 kilometers. So it's a short, long baseline. It's a long baseline experiment, but this is shorter than Dune. And then a very large FAR detector. The Hyper-K FAR detector will be almost 190 kilotons fiducial water Cherenkov detector. So this is just massive. Dune's strategy is to measure all the long baseline parameters, including the mass ordering in a single data set, and map the oscillation pattern as a function of energy for precision measurements. And so this leads to the choice of the longer baseline of 1,300 kilometers, a broadband beam as opposed to an off-axis peaked beam. and precision emitting FAR detector. So the Dune FAR detector will be a liquid argon TPC that is 40 kilotons or a bit more fiducial, depending on exactly the details of the detector. All right, so moving on, and I should say that, you know, both experiments do both. So Hyper-K will certainly do precision measurements. Dune will certainly measure CP violation. It's just a slight difference in strategy about how to approach doing that. So these are the Hyper-K oscillation physics sensitivities. I've just picked a few plots. You can see, you know, many more details in the Hyper-K design report. So what's plotted here is the sensitivity to observe CP violation. So that means to observe that delta CP is not equal to 0 or pi as a function of the true value of delta. And this is for true normal ordering. And so what you see is that for about half of parameter space, you get really exquisite sensitivity. Like Hyper-K just is very, very good at this measurement on this side of parameter space. But then if you go over here, because of that degeneracy between matter effects and CP violation, if you had only the beam physics, you get significantly reduced sensitivity if the true value of delta lies over here. You recover quite a bit of that if you include the atmospheric neutrinos. And of course, it becomes very nearly symmetric if you have some external constraint on the mass ordering. So if it's already been measured. Over here on the right shows how Hyper-K does with this same exposure for precision measurements. These are the atmospheric parameters, delta m squared 3.2 and sine squared theta 2.3. The red curve is Hyper-K alone, and blue shows the improvement that you get if you include an external reactor constraint. And this is the same plot for a precision measurement of delta and theta 1.3. So moving on to the Dune sensitivities, I said that part of Dune's strategy is to be very sensitive to the mass ordering with the long baseline. You can see that for moderately large exposures here of, you know, 300 to 600 kiloton megawatt years, which is what's plotted here, the sensitivity as a function of delta is just huge. I mean, this is well above 5 sigma for all of parameter space. And in fact, I don't show you the plot, but the mass ordering in Dune would be determined with high significance for all of parameter space with something like 100 kiloton megawatt years of data. And this is the same plot for CP violation sensitivity, where there is good sensitivity to CP violation after about 100 kiloton megawatt years if delta is minus pi over 2. And then you can see here you get to 5 sigma after 336 kiloton megawatt years. Again, if delta is sort of maximal. And for 50% of delta CP values, you get 3 sigma sensitivity after about 200 kiloton megawatt years. So now looking at the precision measurements, these are the same kinds of plots as you saw on the previous page. This is delta m squared versus sine squared theta 2.3. This is for 3 different Dune exposures. And then the yellow blob is NewFit 4.0, which is just sort of the current world average, or a few years ago world average. Now I think NewFit is up to 5.1. And this is the same plot for sine squared to theta 1.3 versus delta. And what you see here is that for large exposures, the measurement of theta 1.3 becomes comparable to the current world knowledge, which is dominated by reactors. So you can compare the Dune measurement with the reactor measurement as a unitarity test. It's important to note that some of the details of the Dune staging is yet to be determined. That's being worked out within the collaboration and with funding agencies. And so the time to reach particular milestones for early exposures depends a lot on that. But it actually doesn't dramatically impact the ultimate sensitivity as long as, you know, the full scope is realized in a timely fashion. And this actually provides an opportunity for more in the community to get involved and possibly expand the scope of Dune as we're looking at, you know, different ideas for FAR detectors that would provide additional physics opportunities as well as additional sources of funding. I want to say a few words about systematic uncertainty because that is a very big deal for these experiments. We need something like few percent uncertainty for the precision measurements that I showed you. And we have uncertainty from neutrino flux, the neutrino interaction model, and detector effects. And impact of biases due to shortcomings in the interaction model, which we know exist, is potentially large. So as an example of this, I show you the Dune CP violation sensitivity, again, as a function of delta. And the solid orange curve is the nominal sensitivity. And then just as a thought experiment, really, we say, okay, what if we took away the near detector? If we took away the near detector and we had a known perfect model, so our model absolutely describes the data, we just are not sure exactly what value the parameters should take, then we would have this degradation in sensitivity, which is bad enough. But if you include biases from the fact that the model possibly doesn't fully describe the data and there's no set of parameters that is the correct set that describes our data, then you really lose, a very large amount of the sensitivity. So both Dune and Hyper-K require sophisticated near detectors taking measurements at multiple off-axis angles to constrain this kind of effect. It's also really interesting that both experiments are pretty different in terms of systematics, different neutrino energies, different target nuclei, different detector effects. So there's hope that, potentially in a future joint fit that could be beneficial. It's also important to note that experimental measurements of neutrino nucleus scattering, development of the interaction models, and event generators will all contribute to the long-term success of this measurement program. So this is a big collaboration among high energy theorists, nuclear theorists, and experimentalists.
5 minutes.
Okay, cool. So moving on to physics beyond the standard model, there's a huge array of new physics scenarios that are being investigated by both the collaborations and phenomenologists. I'm just going to give a couple of examples. So there's sort of two categories of BSM, and one is deviations from three flavor oscillations. So we measured the same oscillations that we were measuring for the three flavor measurements, but now you can consider, are there sterile neutrinos? Are there non-standard interactions? Is there some non-unitarity, et cetera, that is making our data not fit well with a three flavor model? So as an example of this, I'm showing a Dune sensitivity to sterile neutrinos. So this is the delta M squared 4, 1 in a 3+1 model and the theta mu e mixing angle. And you can see here is a Dune exclusion curve with the near detector and the far detector. And here's the far detector only exclusion curve. And I think there's still some systematics to be worked out in this plot, so that it's probably the case that the true sensitivity falls in the middle somewhere. One of the good things about having both of these experiments is that if we do start to see some deviation from three flavor, having measurements at both Dune and Hyper-K with the different energies and the different baselines can help disentangle degeneracies between BSM signatures and three flavor oscillations. So these detectors, we can also look for a number of other new physics signatures. So some examples are neutrino trident rate, dark matter, baryon number violation. And some of these are things that you do at the near detector, some at the far detector, and some both. So as an example of a far detector BSM search, I'm showing here the sensitivity that Hyper-K would expect to the P to E pi 0 mode of proton decay. And what's shown here, which is kind of exciting to think about, is that if the lifetime is just beyond the current super K limit, you would see this sizable signal of proton decay in Hyper-K. Supernova neutrinos, again, there's complementarity among the experiments. Dune is more sensitive to electron neutrinos because it observes it has a high cross-section for the charge current absorption. And so here you see that cross-section as a function of neutrino energy, where Juno and Hyper-K see most of their signal from IBD. And so here's the inverse beta decay cross-section. There's information about both supernova physics and particle physics embedded in the neutrino signal. So we want to measure the time profile, the flavor composition, and the energy spectrum. And here are just some examples of the supernova signals that would be expected at the three experiments. This is also a great opportunity for multi-messenger astronomy, where neutrinos can provide early warning to optical and other observations. Solar neutrinos. So delta M squared 2, 1 from solar measurements and reactor measurements is an important comparison, because you're really measuring the same quantity with super different physical conditions. And so this is the current new fit measurement for delta M squared 2, 1 versus sine squared theta 1, 2. And here you see this is the reactor measurement and this is the solar measurement. So this phenomenology paper was actually written when there was significant tension between these two. And it said, okay, if this tension is maintained and you get the precision expected from Juno and from Dune, see how well you could distinguish these. So that's very exciting to be able to possibly significantly reduce that uncertainty. And then the boron-8 and ATP neutrinos also probe solar astrophysics. So again, there's astrophysics you can do here. So both experiments are expected to have some sensitivity. Here's a plot of solar neutrinos at Dune as a function of energy. And you can see there are very large backgrounds here, but you can start to see the boron-8 and the ATP signal potentially being visible. And all of the details here depend on detector resolution, thresholds, cosmogenic and radiological backgrounds. It is a hard measurement, but it looks like it's something that will be able to happen at these experiments. So there's many, many things going on in neutrinos that I haven't had a time to talk about today. Here are a few links to things that you might be interested in. So to summarize, we are already in the precision era of neutrino oscillation measurements. Most of the parameters are known to 3%. Juno expects to reduce some of these uncertainties to better than 1%, which is very exciting. The current generation of oscillation experiments have interesting results on mass sorting and CP violation, but no definitive answers yet. We expect major experimental advances in the next generation of long baseline experiments. There will be thousands of events as opposed to tens or hundreds like we're seeing now. 5 sigma level sensitivity to CP violation, precision measurements of the oscillation parameters, including delta, and significant sensitivity to physics beyond the standard model. I haven't had a chance to talk about it today, but people are already thinking about the next and next generation as well. Systematics are critical, and this especially is important that we collaborate with neutrino and nuclear theorists and do these standalone experiments to measure hadronization and neutrino interactions. And finally, neutrino oscillation experiments enable a broad physics program of astrophysics and BM-SIM searches as well. So I'll just leave you with some pretty pictures from the world of neutrinos. Thank you.
Thank you very much, Elizabeth. This is a very comprehensive review. Are there any questions? Okay, I don't see any. Well, please use Mattermost if you come up with a question during the off talk time. Thank you very much. Let's move to the next speaker. The last speaker of our session today will be Becky Chislett. She will be talking about future muon initiatives, and she is representing University College London.
Hi, I'll just share my screen.
I'll give you a 5-minute warning.
Okay, thank you. Okay, so I hope you can see that. So I'm going to be talking about the future of muon physics. Well, I'll try to include as much as I can. There's a lot going on in muon physics at the moment. And so this kind of follows on from Mark Lancaster's talk in the Monday plenary session, where he was talking about the current muon experiments. And so I've stolen this slide from him. This shows in red the experiments that he talked about, the ones which are currently taking data. And I'm going to talk about the ones in blue, which are up and coming experiments, and also talk about some other ideas which are not yet concrete, but should be coming up. So you can see that there's a vast muon program all across the world here. So muons provide an interesting opportunity to look for new physics, and we tend to do this in 2 ways, one of which is making high precision measurements and comparing them to standard model predictions, and the other is to look for processes which are essentially predicted not to happen, so look for the appearance of those signals. And at the moment, we have the availability of intense muon beams. So I've shown 3 different facilities which provide these beams. So we have the Fermilab facility, which you can see in the top right, and that has this new muon campus, which houses the G-2 and mu2e experiments. And so they've repurposed the accelerator here and used the old antiproton complex as the delivery ring for G-2. And then we also have the muon beam at PSI. So this is a DC beam as opposed to the Fermilab and JParc ones, which are pulse beams. And at the moment, this provides 10 to the 8 muons per second to experiments there. And then there's also the facility at JPark. And so this has a similar number of muons produced to Fermilab, about 10 to the 10, but these are both pulse beams. So muons are interesting because they have a reasonably long lifetime, but then they do decay. And so this lifetime enables us to study them. And they're a second generation particle. So this is a unique opportunity, but also means that they have a mass advantage over, for example, the electron, which provides an interesting probe into new physics models and allows us to reach high mass scales. And they also have good production and decay properties, which we can utilize. So this means that we can produce a polarized beam of muons through the pion decay, and we can also use the decay properties to study various things. So those are the facilities that are available and being used at the moment in muon experiments, but they also have proposed upgrades to all of these different accelerator complexes. So at Fermilab, there's going to be this new PIP2 beam, and that's an 800 MeV beam, which provides good opportunities for the mu2e experiment. And then there's this high intensity muon beam at PSI, which would increase the number of muons from 10 to the 8 per second to 10 to the 10 per second. And then also there's going to be this H line at JPark, which should start soon, and that will be used in the JPark G-2 experiment to produce this super cold muon beam. So as I said, this is kind of following on from Mark's talk, so I've stolen his conclusion slide here as the kind of starting point. So he showed the latest G-2 result, which is obviously very interesting and shows this 4.2 sigma discrepancy between the theoretical prediction of the muon G-2 and the experimental measurement. And G-2 is currently still taking data and has a lot more data to analyze. So hopefully this will resolve this discrepancy and see if this really is a sign of new physics. And there's also all these other experiments which will have data within the next year and produce results. But for this G-2 experiment, it's obviously important that we try and measure it in a different way, and that's what's being done at JPark. So we have this spin precession equation that you can see here, and the Fermilab experiment gets rid of this electric field contribution. So it uses the electric field to focus the beam, but cancels it out by selecting the momentum. So we run at the so-called magic momentum. The JPark experiment does this in a different way by not using an electric field at all and not requiring this focusing. And so in order to do that, you have to have this ultra cold muon beam so that you don't have the divergence. So the way they do this is by producing these surface muons and making muonium and using a laser to then strip the electrons to produce this ultra cold muon beam, which is then accelerated, and that produces very low vertical dispersion. And that means that you don't need the electric field to focus the beam. So this is kind of what the experiment looks like. So this is the beam line, which I showed you, this H line at JPark, where they produce the muons, and then they get put into this small magnet with a tiny radius. And then they have tracking detectors in the middle to detect the positrons from the decay. And based on that, they use the same principle that the Fermilab experiment uses. And this small size of this magnet means that they can get high field uniformity, which is also really important. So the phase 1 for this is expected to start in 2025. And the aim of that is to reach a similar uncertainty to the run-1 result that Fermilab just produced. And so that would be a really important cross-check using completely different experimental technique of the result that Fermilab has obtained. In addition to this, we can measure the muon EDM, both at the Fermilab experiment and the JPark experiment. And so an EDM is similar to the magnetic dipole moment, except that in the standard model, it is predicted to be essentially 0. So any observation of an EDM would be a sign of new physics. And it's interesting because this would provide an additional source of CP violation in the standard model. So in the plot here, I've shown the current limits and the standard model values for various different EDMs for the electron, muon, proton, and neutron. And you can see that the limit on the electron is really low, and actually they improved upon this limit by a factor of 10 not so long ago. And this cut into a lot of different beyond the standard model physics models. The muon EDM limit is much higher. The limit was set at the Brookhaven experiment for the muon G-2. And using standard mass scalings, you'd kind of rule out a muon EDM, but there are many models that have non-standard scalings, and therefore you can start cutting into phase space by improving upon this limit. So if we have an EDM, then it modifies this spin equation that I showed. So we have the magnetic dipole moment contribution, but the electric dipole moment produces this additional term. And this is essentially perpendicular to the magnetic field. So what it does is it changes your spin precession and adds this vertical component, which is π/2 out of phase with your normal spin precession from the magnetic dipole moment. So to look for this, you want to look for a vertical oscillation. And this is what they did at Brookhaven. But at Fermilab, we have the advantage of the new tracking stations, and you can see the various limits that we could set here with the overall aim of reaching around 10⁻21 e centimeters. And using this exact same method at J-Park, they would aim to reach the same limit there. But there's also a proposal for a dedicated muon EDM experiment at PSI. And this uses the technique where it's called frozen spin. So taking your spin equation again, you can kind of play around with this equation, cancelling various different terms out in order to focus on different parts. So in this case, you would choose your electric field such that it cancels out this spin precession term from the magnetic dipole moment and leaves you only with the electric dipole moment precession. And so this has a similar setup to the J-Park experiment, where you have low energy muons injected into a small ring with a tracking station in the middle. And then you choose this electric field to cancel out your spin precession and just look for the oscillation due to the electric dipole moment. So with this dedicated experiment, that would take us down to 10⁻23. So that's 2 orders of magnitude better than Fermilab is aiming for. And you can see how this starts cutting into these various different beyond the standard model ideas in the plot on the right. And then with the high intensity muon beam that's going to be built at PSI, that would potentially improve this by an additional order of magnitude. I think there's also a proposal at J-Park to use a similar technique with this frozen spin, so they could also measure that there because it's a very similar setup. Then also at this experiment at PSI, it has the potential to measure the G-2 as well in the same way as the J-Park experiment. As an aside, so obviously this isn't muons, but while we're talking about EDMs, I just wanted to mention a potential proton EDM experiment that's been proposed. And here this would use an all-electric storage ring, again playing around with the spin equation and cancelling out this term by choosing your momentum correctly, and leaving again only the precession due to the electric dipole moment. And with this technique, you would be able to improve upon the limit on the proton EDM by 5 orders of magnitude, which is a huge amount, and again, can cut into many different physics models. So now to move on to charged lepton flavor violation. So there's all sorts of different experiments that are looking for charged lepton flavor violation in different channels. So this is the neutrinoless conversion of a muon to an electron. And this is allowed in the standard model as shown in the diagram here due to neutrino oscillations, but because of the very short scale in which the neutrino would have to oscillate, it's 10 to the minus 50 in the standard model, which is well below what we can reach with experiments currently. So any observation of this would be a sign of new physics. And there's all sorts of models that can produce this. So it probes a wide range of different physics models. And there's 3 different channels that we look for this in. So MEG2 looks for it in conjunction with a photon, and Mark spoke about that on Monday, so I'm not going to talk about that one. But then we also have mu2e and COMET, which look for this in the field of a nucleus, and mu3e, which is the photon converting to 2 electrons, so it looks for 3 electron signal. Essentially, this is a monoenergetic signal that you're looking for. So here you can see the kind of levels that we reach and how far we can push down with these different experiments. So mu2e and COMET are looking to improve upon the limit by 10 to the 4, as is mu3e. So this is a huge increase on the current limits we have set. And you can see in the plot here that this reaches very high mass scales up to 10 to the 4 TeV. And it's the conjunction of all these 3 different channels which allows you to kind of have some ability to differentiate between the different new physics models. So if you saw a signal in one and not the other, then you'd know where you are along this x-axis.
4 minutes.
So the mu2e experiment looks for this through the release of a monoenergetic electron and COMET as well. And this comes at the end of a very steeply falling background. So you need excellent momentum resolution essentially to pick out this signal against this background. And so all these experiments need this excellent momentum resolution. You can see the mu2e experiment here. So this is how it works. You inject these 8 GeV protons onto the production target and collect the pions, low energy pions going backwards, and put them through this transport solenoid where they decay to muons and then get stopped on your aluminium stopping target. Then they have the tracker with this hole in the middle so that you only detect the electrons of the energy that you're looking for and therefore get rid of the backgrounds. And then there's a calorimeter, and in addition, there's a stopping target monitor, which measures the X-rays from the muons that are stopped so that we have the normalization for the experiment. Then there's also a proposal to upgrade the experiment mu2e2, which would use the new PIP2 beam at Fermilab, which is 800 MeV, which is a better energy for the production of these low energy muons, and also has advantages such as narrower pulses, less variation between the pulses, a higher intensity and a higher duty factor. There's also upgrades to most parts of the experiment in this proposal in order to cope with this different beam, and simulations and prototypes for that are ongoing at the moment. Then there's also the COMET experiment, which has 2 phases, phase 1 and phase 2. You can see that this looks very similar to the mu2e experiment. So here in phase 1, they just have this single turn. So this has higher backgrounds, so makes it more challenging. And this uses a cylindrical drift chamber here. And that plans to start data taking in 2023 to produce a factor 100 improvement on the current limit. Then they'll upgrade this to phase 2, which has this double turn with the S shape, and this allows for a much purer beam. And then they use a tracking detector here because of the lower rates. And that would then improve by a further factor 100 to the 10 to the 4 that mu2e also wants to achieve. There's also the PRISM experiment, which is a proposal to increase this further by having even better background reduction by including this ring, and so making a purer beam and having a lower rate on the detector. And so this should allow them to push down to sub 10 to the minus 18 sensitivities if this goes ahead. The mu3 experiment looks for the signal with 3 electrons. And so in order to detect this, they need excellent momentum resolution and good vertex reconstruction, as well as excellent timing information. Because again, you can see that this comes at the end of a very steeply falling background, the same as before. So they reconstruct the mass from the 3 electrons that they detect. And this is what it looks like. So they have this target and they have this DC beam from PSI coming in and hitting the target. And then they have the pixel layers, the fibers for timing, and then they have this recoil station. So they started their integration run in 2021, just with this central part. And then this is going to continue through 2023 until they start taking data with the full setup in 2024. So this phase 1 should have 1,000 times improvement on the current limit. And then they'll again use this high intensity muon beam that PSI is building to achieve a further factor of 10. So a total of 10 to the 4 improvement on the current limit. So then I just wanted to mention some future muon projects, which I don't really have time to talk about in any detail, but these are proposals that have gone in. So there's pi nu xe, which is a proposal to measure the difference, the ratio between the decays of pions to electrons and muons. And this is a precision tested standard model. The theoretical prediction for this is very precise, but the experimental measurement hasn't reached those levels yet. And so it would bring this in line with the theoretical uncertainty. And then, as was mentioned earlier, there's also proposal to build a muon collider, which comes with various challenges from the muon decay, basically, but they don't suffer from the synchrotron radiation problems that the electron-positron colliders do. So this is an interesting prospect to reach high energies in smaller rings. So that's also a proposal that's being considered at the moment. So then, just to conclude, this is a very exciting time in muon physics due to the availability of these intense muon beams that we have, and there are upgrades that are planned for those, which means that we can push even further. So there's many experiments that are ongoing, and we'll get results in the not too distant future, as well as proposals for further experiments after these have concluded. So thank you very much.
Thank you very much, Rebecca. Very nice talk. Are there any questions? All right, so let's, I don't know who was first. Let's start with Chris. Hi, Chris.
Thanks, Alexei. Thanks very much. Really nice talk. Great, a really interesting field. If I remember correctly, G-2 and mu2e can't run at the same time, right? So what's the plan for the next few years in terms of operations of these facilities?
So as far as I know, G-2 is currently in run 5 and will have run 6, and then the beam will be transferred over to mu2e. I mean, so it takes a bit of work to transfer the beam across, but there are also ideas to allow a quick transition between the two. So if mu2e was commissioning and then didn't need the beam for a while, potentially it could get transferred back to G-2 if we can implement these things to make it a quick changeover. But yeah, essentially the main plan is that G-2 will have run 6 and then the beam will go to mu2e after that.
And a run is a year, is it? Or?
Yeah. So Fermilab start the shutdowns over the summer. So it starts in roughly October and finishes around June, July.
Many thanks.
All right, thank you, Nicholas.
Yeah, thank you for this nice talk. Actually, I was wondering in your slide 21, when you measured this, you mentioned this pion decay experiment. And I was wondering, the motivation to do that, is it because you think you are sensitive to new physics, or you think that the precision measurement will fix some kind of correction in the standard model that is very difficult to calculate?
So I'm not heavily involved in this, but there's a proposal that's been put in. I think it's basically a test of lepton universality. And when you have a precise theoretical prediction and it's much more precise than we can measure, then it's I guess interesting to measure it to that level of precision and compare the two to see if there is any new physics and you know whether lepton universality holds, I think.
Okay, so it's beyond standard model physics. Thank you.
Yeah.
All right, thank you. That's precisely right. By the way, that's exactly what they're trying to achieve, to study lepton flavor universality. Are there any other questions? I actually have a question, if I may ask. We still have a little bit of time before official end of the session. So you talked about JPark muon production, which essentially goes through production of muonium first.
Mm-hmm.
Do you know if there are plans to do muonium oscillation, muonium antimuonium oscillation experiments, since they have lots of muonia?
I'm afraid I don't.
Okay.
Sorry.
No, that's all right. Maybe someone knows.
Yeah.
In the audience? No? Okay. This is, we still have 5 minutes. So if anyone has questions to any of the speakers in this afternoon. I really don't want to finish my session 6 minutes earlier, just like I did last time. Normally people run over time. This is a very interesting phenomenon here. All right, if there are no questions, I might actually make a comment to Rebecca's talk. Sorry, you already removed it. So on page 13, right. So this picture on the right, I mean, this is actually an illustration of what might happen if you have only two interactions, you know, dipole and a contact. I mean, the reality is actually that I don't know of any new physics model that has this particular feature, especially with this constant kappa. I mean, normally you have several contact interactions, and of course there's possibly a dipole interaction. So the picture is much more intricate. I mean, you would have more kappas, so to speak. So this is just a nice illustration of what or the relationship between the dipole contribution and the contact contribution.
Yeah.
All right, thanks. Any other questions? If not, well, we'll have again, we still have Mattermost, and we'll have 4 more minutes for the break. I don't know if Marco has any comments. Again, I don't know if I should apologize for ending this earlier.
No, thanks very much for sharing, Alexei. Thanks for the great talks, and thanks for staying on time indeed. I think throughout this has been very well, and we'll restart at 1/2 in most time zones. Should be 34 minutes from now, and we'll have the last session then.
Thank you.